Attendees are in listen-only mode.
Well, good afternoon, everybody, and welcome to today's webinar, Optimizing CAD Files for Additive Manufacturing. My name is Rob Romanowski. I'm the Director of Operations for 3HTI, and I'm joined here today with Bruce Bodnick, 3HTI's Senior Technical Director, Gary Hoffman, 3HTI's Principal and Vice President of Sales, and also Sean Kroger from SolidThinking, who is going to take us through a couple of SolidThinking tools which help to better optimize your CAD files for 3D printing and additive manufacturing. So a couple of housekeeping items before we get started. Everybody's going to be on mute during the webinar. If you have any questions, feel free to type those at any time in the dashboard. We will try to answer those questions as you type them in, but they will definitely be answered by the end of the webinar. So without further ado, I'm going to pass everything over to Gary Hoffman so we can get started. Gary, it's all yours.
Thank you, Rob. And Bruce, just as a quick check, can you see my screen?
Number one reseller on the planet?
Yeah, I mean, is there any menus and stuff like that just to verify?
Yeah.
We're good.
All right, sounds good, guys. But thanks again. My name is Gary Hoffman. As Rob said, I'm the principal of 3HTI. And we're here to talk about a bunch of stuff, so we're going to kind of move at a bit of a lightning pace. Normally, we get on and get off in about an hour, and today I would anticipate it's going to take a little bit longer. But the order of the program is going to be, I'm going to show you a couple slides and give you a very quick background on 3HTI and introduce Sean Kroger. Sean is going to talk about SolidThinking and a couple of their products. One of them is Inspire. And then I'm going to jump back on, give you a quick overview of Markforged and Envision Tech, and then Bruce is going to finish us off with doing a live web presentation. I say webcam of both printers and operations. So we got a full agenda. But in any event, as a company for 3HTI, what we do is we're not really a printer purveyor or a software purveyor. We're really looking to solve people's problems. So what happens is typically somebody will come to us, and a lot of times the problem that they come to us with is different, or the solution they think they're going to wind up with is different than what they actually wind up with. And what we do is we really get in and say, hey, what's causing the problem? How do you fix it? And sometimes it can be something completely different. So as a company, we have a whole cadre of products that we take to help them solve their problems. Some of it is service, some of it's process, and ultimately what we're trying to do is we're trying to improve a company's time to market, improve their quality, and reduce their cost. And, you know, for example, one of the companies we've dealt with in the past year that we have some team members going to a meeting tomorrow, their problem was actually they wanted to buy a piece of PLM software, and when we went in and looked at it, we said, what's wrong with what you have? And lo and behold, if they changed their process a little bit, it would enable them to reach their goal, which was to develop twice the number of new products in a year. If anybody knows anything about product development, a company makes profit off of new products that are coming to market. So, you know, our commitment is that we want to listen to what your requirements are. We want to set you on the right path. And ultimately, because we have a variety of different tools to sell, we want to select the tools which fit your customer's need the best. And then ultimately, if you don't have the right minds and the right people to go in and make it work, then the tool is worthless, and that's what we have. So we focus on product development, we focus on simulation, and this is using software tools to actually do simulation, which is part of where Sean comes in today. We work with traditional manufacturing, which is more subtractive, and a variety of different tools around that. Product lifecycle management is a very large practice of ours. And then lastly, 3D printers and additive manufacturing, which is a big deal today. Our belief in 3D printers is ultimately they are really something that you can make something with. And I just got done watching a YouTube video where we have a company by the name of Dixon Valve that is actually making parts that be able to go on to machines to either hold parts in production or be able to actually use it in an automated part changer. So we look at 3D printing as something that's not just a novelty, but something that, you know, ultimately saves time and saves money, perhaps over traditional manufacturing. So what's really good, I mean, we're not a huge company, But what's awesome is that we have the who's who in the zoo in terms of nameplates that actually purchase from us. And I'm very, very proud of that. So in the last 6 months or less, companies that are on this list have chosen to do business with us. And some of these companies are for the 3D printers, some for software, some like DuPont, for example, are for both. And I think that's really where it fits in very well, where we can actually be a trusted partner and be able to sell multiple components of an entire end-to-end solution if in fact that's what somebody desires. So we sell a whole bunch of products, as I mentioned. We sell Markforged, we sell Stratasys, we sell Envision Tech, so we're going to talk about Markforged and Envision Tech today. We just had a request for information from Venezuela, for example, for multi-DNC, which is something that actually feeds numerical code to the machine tools. Controls Pro Studio, which is something that automatically allows you to turn your mechanical CAD software into a configurator. NC Simul, that actually lets you simulate NC toolpaths after they've been post-processed with the machine. Keyshot is a rendering software that allows people to create videos and realistic renderings. We do sell Mentor's complete line of products, but ultimately focus on their fluid flow or computational fluid dynamics that include FlowTherm, FlowTherm XT, Flow EFD, which actually hooks onto a lot of name brand CAD systems to be able to do really a full featured general analysis for fluid flow, for thermal, things of that nature. Moldex 3D for analysis of actually mold designs. We sell PTC's line of products, which include Creo, Mechanical CAD, Windchill for PDM Link and Project Link, Arbortex for technical publications, MathCAD for engineering equations, Simolia, which is actually a tool from Dassault Systems that does very high-end implicit and explicit analysis to be able to analyze what something's going to do after you've designed it. So what it brings, the last but not least here, is with SolidThinking. So SolidThinking is actually a division of Altair Computing, and they have a couple products I'm going to let Sean explain to you. But what I find really interesting or intriguing about what SolidThinking does is that when I went to design school, they always used to say form follows function, form follows function. You were like, okay, and you thought a little bit about the function. But ultimately, the way things work today is, let's say use Creo or SolidWorks or CATIA or whatever. Ultimately, what happens today is somebody comes up with the form. They might be thinking about function, but they really don't have any way of understanding what the function's going to be. So sometimes they simulate it with Simolia or they use Mentor. And then what happens is by the time we're done that, we find out, hey, you know what, this thing, no matter what you do, we can't get the problem to really solve within the criteria that you're looking for, and it becomes an absolute mess. So what SolidThinking does is really starts out with function in mind, and you put in some functional characteristics, and ultimately it takes the geometry and it actually uses human bone growth algorithms to do generative geometrical design to actually come up with some really, really cool geometrical solutions that a lot of people wouldn't think of. And I think what's neat about it is it works with sheet metal, it works with structural steel and skids, it works with plastic, all kinds of stuff. So the notion here today is that that if you have something that you really don't have a lot of limits in terms of what you can actually print, that would be something that is manufacturable, then ultimately what happens is that you would use SolidThinking because now geometry isn't as much of a challenge. So with that, I'm going to turn it over to Sean Kroger from SolidThinking. And Sean, I think you have the con, as they say.
Thank you very much, Gary. Can you guys hear me okay?
I can.
Yeah. Excellent. Okay, so I appreciate that info and or the introduction. As Gary mentioned, my name is Sean Kroger. I'm from SolidThinking. Been here about 3 years. Previously was with SolidWorks, managing all the simulation business. And I think the preface that Gary laid out is really accurate. You know, if you look at 21st century design versus the 21st century design, right? Form follows function is exactly how people design things, right? So this is what the internet says form follow functions mean, but it's really creating a shape that's going to result in the intended function or purpose. 21st century design I like to call form follows forces. And I believe it was one of the 3HTI guys that first mentioned this to me, but it absolutely is a process in which you use the load cases to design what your shape should look like. So this was just a podium example that we went through to show you how, based on the forces of someone leaning on it or the gravity associated with it, this design would be modified to meet that form. So really what SolidThinking Inspire is all about is it's a tool for design engineers and architects to come up with concepts. So imagine using this before your detailed CAD, and it's because of the organic nature of these simulations, it really comes up with these organic shapes that fit very well for additive manufacturing. But ultimately it helps companies make parts much faster than ever before, because instead of starting with a blank sheet, you start with an ideal shape. Right? It's smarter because you're designing it for the loads that you're creating, and ultimately this results in much lighter parts. So lightweighting is really a byproduct of this process, but it's one of the main attractions that companies have is how do we take material out of our designs, use less material, and still maintain that same level of performance. So the way it works is you simply provide the packaging space. So where can material exist and what are the loads that are going to be applied? And then Inspire is going to come up with this ideal shape. As I mentioned, it results in lighter designs, but I've also seen it drastically reduce the design cycle because you can cut down on those iterations you go through between detailed design and validation. So instead of going back and forth between your simulations and your detailed design or your physical prototypes and your detailed design, you can do it, you can validate it once because you started the process using analysis and simulation as the primary driver. So it's an upfront concept design tool. You can take your existing CAD files and modify those, make them available for 3D printing, or to take advantage of the freedom you get in 3D printing. But you can also meet more traditional manufacturing constraints like cast designs, extruded designs for sheet metal. So it's not just for 3D printing, but we have gotten a bunch of traction in that space. It interfaces with all the existing CAD products, so you can very easily bring in your existing models and then create a solid, take that back out to your CAD package and use that as the starting point for your detailed design. There's a ton of companies using Inspire. Obviously the automotive and aerospace companies have kind of were the first to adopt this to lightweight air structures, to lightweight automobiles and make them more efficient. But we see more and more companies like Zaha Hadid, an architectural firm, using Inspire to come up with bridge designs or building facades, to companies like Polaris, lightweighting snowmobiles. There's really a broad set of customers out there using these tools. So as I mentioned, when you look at the concept development process today, and as Gary mentioned, that's really how companies make money, is develop new concepts and new products, and that drives their profitability. And that process starts with either a napkin sketch, maybe you open up your CAD package and start doing a 2D sketch. At a certain point that moves to a more detailed design phase, and then you get to that validation where you're either simulating or building physical prototypes to make sure that that design is working as expected. What happens is oftentimes you go back and forth, right? So there's many iterations between detailed design and validation before you actually get to production. So with Inspire, you're going to start that detailed design phase with a solution. And ultimately, that's going to shorten time to market. So this is a huge benefit for companies. If you want to double the amount of products you develop in a year, you've got to figure out how to shorten that time to market. And Inspire is a huge benefit for companies to do that. So let's kind of talk through the workflow. I'll show you a quick example of how this product works. And then if you have any questions along the way, please type them in and be happy to answer those. But here's an example of how to redesign a robot with Inspire. We can very quickly do a full assembly level analysis, and you can see what Inspire would do to this type of a design. So if I look at just how do I optimize one of these components from an existing CAD design, it's pretty straightforward to bring that into Inspire. That very first step in Inspire is all about creating a packaging space. So oftentimes you'll remove your features, roll back to the maximum volume you're working with. This can be done in your CAD package, or there's a lot of tools in Inspire to help facilitate that. You apply your load cases and you specify how it's connected to the other components, and Inspire is going to generate an optimized shape for you. So in this image here, you can kind of see Inspire has removed material where it doesn't need it, but has kept the components or the structure that's required to support the forces that were defined. Now this is a more organic design, probably ideal for additive manufacturing, but as I mentioned, you could also use those same loads to generate a design that could be cast or maybe extruded. So there's maybe a machine type design. So there's a lot of different ways that that same input can come out with different results based on what type of manufacturing you're doing. Now before you actually start your detailed design work, one of the biggest benefits I see in Inspire is the ability to validate that concept up front. So, you know, maybe you created those 4 different designs we just looked at and we want to figure out which one's the best one to move forward with. Here we can do comparison studies on things like displacement, understanding tension and compression, factors of safety, what is the von Mises stress throughout your components. And again, I haven't even opened up the CAD package to start a detailed design. So you're bringing analysis in at the very earliest stages. One of the technologies that was originally in our Evolve product we've now added to the Inspire tool is something we call polyNURBS. And polyNURBS now allows me to take this wrap or this shape and wrap a design directly over top of it. So if you're going straight to 3D printing, you can very quickly create a smooth surface by wrapping your geometry right over top of the results that Inspire gives you. And I'll show you more in depth on how you would do that, but it's been a very successful capability that was brought into Inspire, and a lot of companies doing 3D printing are using this now to simply just create their shapes from the Inspire results. So, you know, in this example, this robot, we took 30% of the weight out of it. You can get away now with smaller motors to do the same type of performance you had before, and, you know, use less energy, so it's more cost effective. And that's really the power is companies are able to make parts that are lighter, that are stronger, and actually last longer, because topology optimization evenly distributes stress throughout your component. Typically that results in much higher fatigue performance. If you look at the interoperability and how these products work with other CAD packages, we can import geometry directly from SolidWorks, Unigraphics, CATIA, Pro-E, both Creo and Wildfire versions. We are based on top of the Parasolid kernel, so we can read in Parasolid geometry, as well as your more standard STEP, IGES, and ACES formats. We run on both Windows and Mac, and then once you've created a result, you can actually solidify that result and then write that out as a Parasolid, STEP, IGES, or if you're going straight to 3D printing, you can write out an STL file as well. So I've got a few examples I just wanted to share with you before I pull up the software on how people in the additive manufacturing space are using Inspire. First example here is from a company called Hardmark over in Australia, but it gives you a good idea of how you would take an existing design of this piston and then use Inspire to additively manufacture the underlying components. So you start with defining the forces here on the top of the piston. You fill in that entire bottom area and tell Inspire that, keep the material that you need for the forces that are being applied. And this is what Inspire comes up with. Now you can use that same polyNURB technology to smooth that out and create a smooth final result, send it right to your metal printer. Here's an example from Empire Bicycles and Renishaw. They joined up and created the first 3D printed bicycle frame. If you've been at any of the conferences, you've probably seen this around, but they started this process with an existing bicycle design. So they took that aluminum design that they had, brought that into Inspire, and said, all right, I'm going to change the material to titanium and see how that changes the layout of the structure. So Inspire came back and said, well, based on your titanium material, you should change the structure to look like this. And then they finished that out and sent it to a printer as well, making the first 3D printed bicycle frame. Also, this part's in space right now on the Sentinel-1 satellite. Went up in space last year. This was done with EOS and RUAG. But here you had an existing sheet metal design that was designed for this antenna holder. They took that into Inspire and created this structure here. Increased the natural frequency, took 43% of the weight out of it, and had better structural performance all around with only with 60% of the material. So this is the type of achievements that you can get when you start optimizing your shapes. So I'm going to stop there. I'm going to pull up the software and kind of walk through it. We're going to basically talk how we can go from a design like that to a design just like this very quickly and easily. So that's the workflow we're going to look at. Again, we can start this design by simply importing any geometry. So I can say File, Open. I can look at Inspire files or CATIA, Parasolid, Pro-E files. Whatever type of geometry you have, you can use as a starting point. Here I'm just going to bring in a Parasolid file. And you can see all this in this Parasolid file, all the existing features are in this model. So one of the things you want to do with Inspire is to simplify that geometry. We've got a lot of nice tools to help with that. So for example, if I wanted to get rid of all the holes in this model, I can select the Holes tool and then just deselect the holes I don't want to remove. So let me select these here quick. And let me deselect the ones on the other side here. And then all I have to say is, you know what, fill all those holes, remove all of them. And so Inspire goes in and just blows away all the rest of those features. Maybe I want to get rid of the fillets on the edges to kind of expand that packaging space. Simply click on rounds and start removing your features directly from there. And now we've set that as our design space, right? So everything here in red will be touched by the optimizer. Everything in gray is still part of the analysis, but it's not going to be touched by the optimization process. Once you've set up your design space, it's really about defining how things are connected to each other. Right? So I can fill in connections, create hinge type constraints very quickly. Just add those into my component. I can do things like maybe I want to just put a pin in this hole here, pin in that hole, and I want to tell Inspire, you know what, this pin is, I don't want this last one to rotate, so I'm going to lock that pin so that it can't move. Okay, so once we've got the constraint set up, you also want to set up your load cases. So with Inspire, you can set up as many load cases as you'd like. Maybe we just want to apply some forces to these faces, and that's my first load case. But I can also say, you know what, I want to set up another load case here that includes a side load, right? So I could just put a second load case in. You're going to get a single result for all of the combined load cases inside of Inspire. At this point, you could, you're ready to run an optimization. When you run an optimization, you can either maximize stiffness or you can minimize mass. So when you maximize stiffness, you specify a percentage of this red space you want to keep, and Inspire is going to make the stiffest possible part within that design space. You could also say, give me the stiffest possible part and the highest first natural frequency, or I want a first natural frequency above, say, 200 hertz. So if you're designing a component for an automobile and you want to avoid road load noise, you could say, I want that first frequency above 100 hertz, and that pretty much will avoid any of the excitation you might get from the road. The other optimization is to minimize mass. So when you minimize mass, you're actually using the material properties and a safety factor. So traditionally when you design something, you create a part, you run it through your FEA, and you find out you have a safety factor of 10. And you sit there and ask yourself, well, I definitely over-designed this. How can I remove some of the material? Inspire works in the opposite direction, where you actually set your safety factor, and then it creates a part to meet that safety factor. So if I set this to a factor of safety of 1.2, it's going to take all the material away that it doesn't need to meet that 1.2 safety factor. You're going to find gravity, specify what load cases you want to include in that simulation, and then just run that. It takes about 5 minutes to run, so I'm going to open up the end result. Right? But this is the shape you would get with no shape controls based on that same loading scenario. So with the Shape Explorer, you can quickly see how material is removed from this design. Right? I can also do things like, all right, this is great for additive manufacturing, but what would happen if I wanted to make a cast part? So I could use these shape controls here inside of Inspire to, under the Structures tab, you can do single draw shape control, split draw shape control. I could do an extrusion shape control, which is going to give me a constant cross section. We can include things like planes of symmetry, cyclic symmetry. So a lot of different options to get a design from Inspire. So if you look at how these different shape controls would affect that result, I can see here this would be the single draw cast design where I'm pulling a die from one side versus a split draw cast design with no holes. Kind of looks like an alligator head, so more of an I-beam type design. To a water jetted cross section where I wanted a constant extrusion thickness. Again, all the same inputs, simply changing the design parameters. And here would be a more machinable design, something that you wanted to, maybe mill out or do as a split draw casting. But you can see all these have the same inputs, simply a change in the manufacturing type. Now, as I mentioned, another huge benefit is wherever I'm at on that slider bar, I could hit this Analyze button, and that's going to run an FEA of this new design I just came up with. So in the FEA, I could look at, okay, I've got the organic design. How does that perform? Maybe I want to look at factor of safety, von Mises stress. I could ISO clip on where the highest stresses are in these components. You can do things like min and max, do callouts, or as you mouse over, you can see what the stress is at any point. A lot of different things, but what I like the most is the Compare Results tool. So Compare Results lets me really quickly compare apples to apples on my designs and understand what's the best design to move forward with. So I can see this chart down here at the bottom of all the different designs that we just ran. And we can see, okay, what's the minimum factor of safety? Well, here was the lowest factor of safety, and that came from the original gripper part. Right? So it was the heaviest part, lowest factor of safety. Now if I go down and look at, what's the lighter, the lighter designs, I can kind of see, based on the factor of safety, where each design came in. I could add things like, tension and compression, add that as a chart. If I had done frequency analysis, I could look at the first natural frequencies of these components. And it really helps me to decide which design I want to move forward with. Now, when you're ready to move forward with your CAD into the CAD products, you can take these results, and this other button here, instead of Analyze, it's the Fit button. And what the Fit button does is it creates a solidified parasolid geometry that you can then write out to your CAD package, and then use that as a starting point. So if you fit this, now it's going to fit it wherever I'm at on the slider bar. So say I got a result that wasn't fully connected, I just move that slider bar until everything's connected, and then I hit Fit. Now, at the beginning of 2016, we also added the ability to create an organic design directly around this shape. So under the Geometry tool, we added this new feature here called PolyNurbs. And PolyNurbs has been one of the coolest tools I've got to play with because it allows you to very freely create smooth surfaces right over top of these shapes. So you can see how my cursor is interacting right here with the geometry and the cross section. I select one end, I move it here, I'm now creating blocks that are basically wrapped over top of those shapes. Maybe I'll start coming down this way. I can do things like maybe I want to create a bridge between these two surfaces. So you don't have to follow the design exactly if you want to create other features. But all these components can be just pushed and pulled. I could take the points and start moving those around. Maybe I want to take the end and start adjusting that. Maybe I'd like to make this, instead of a round design, more of a sharp corner. Right? So I want more of a flat surface, if I will. I can just change the continuity on those and start creating a very flat type design. Again, any of these points and edges can be moved around and adjusted as necessary. But it allows you to very quickly get into a final design. It'd probably take you about an hour to create a final design, but here's the one I created from this design a while ago. There you go. So if you look here, here's the final polynerve design. So basically just using the structure that Inspire came up with as a guideline, you're able to create this geometry right over top of it, and then can run the FEA on that as well. So we can see how this design performs. And I can look at, again, von Mises, displacement, factor of safety, tension and compression, major principle. So you have all the same capabilities that you do on the geometry that was created with your final design. And then this is actually a perfect candidate to be 3D printed. So we've got a lot of example cases of this being 3D printed, but this same process can work pretty much on any geometry. And it allows you to really benefit from the freedoms you get of additive manufacturing. So with that, if there's any questions, please type them into the dialog box. I will answer those as we move forward here with the presentation. But I appreciate everyone joining us today. And if you'd like to give this a try, talk to the 3HTI guys, and they'll be able to get you set up with testing it out. So with that, I'm going to pass it back over to Gary.
Yes, pass it back to Gary.
Sounds great, Sean.
I also have uploaded a data sheet for SolidThinking's Inspire into the handout part of the dashboard, so if you'd like to download that data sheet, feel free to.
All right, guys, awesome job, Sean. So I think, if you guys think it's an FEA tool, it kind of is. If you think it's a CAD tool, it kind of is. I think ultimately what it is, it's sort of a hybrid between both. And I think, just to be clear, you really would still need an FEA tool, and you really would still need a CAD tool, but it's really a great way to get started. And as I said, it's all about feedback where you start early, because what we find is when people call us and do simulations, that they need a redesign, and that's not where you want to be. So just we're going to go over a couple things on Markforged, and then we're going to go over a couple things on Envision Tech, and then I'm going to turn it over to Bruce as we kind of make our merry way along. But so Markforged is a company we represent that about 2 years ago came out with a printer that actually prints 3D carbon fiber, but it actually does a heck of a lot more today. So ultimately what they have is they really have, you can kind of see what customers are saying, but ultimately what they have is they use nylon as a basis to print. And so if you think about, if you've ever worked with carbon fiber, what these guys do first and foremost is they print continuous strand carbon fiber. They don't print where you see the weaves and the patches of carbon fiber. So it's different than that. And how they do this is they first put down nylon as a base layer. They actually put down about 4 layers of nylon. Then what they put down is possibly some fiber. And when I say carbon fiber, it can actually be carbon fiber, it can be Kevlar, it can be fiberglass or high temperature, high strength fiberglass, and it actually intersperses it with nylon. And one of the things that Markforged came out with is they actually came out with a new material which they call Onyx. And Onyx is actually nylon, because nylon can be a little bit flexible, which is a good thing because some people want flexible parts. But what it does, it actually has chopped carbon fiber embedded into the nylon. So the way that works is typically you use that as a material that's about 4 times as strong and as stiff as straight nylon. And then you would put in fibers, again, continuous strand fiber, somewhere in the model depending on where you need strength. So recently Markforged came out with a new model called the Mark X, and the Mark X is a printer that is a much larger printer. It's about 13 inches by 10 inches by, I believe it's, I forget the other form, but it's basically 2 point, what is it, Rob?
I believe it's 9.
So 9. So basically what it is it is twice the volume of the standard Markforged printers that we're going to talk about in a second. And those are 12 inches by 5 inches by 6 inches. So 12 by 5 by 6. And this essentially doubles the build volume. But what it also does, it actually allows you to print at 50 microns versus 100 or 125 microns. And we'll go over that in a second. So it's a more expensive printer that is used for higher-ended type parts, and it also has a laser that's incorporated into it. So with the laser, you can actually see if in fact you're not building a part that is accurate to the proper tolerance, or you want to do inspection, it'll actually do that right on the machine. So as I said, I'm trying to kind of roll through these pretty quickly. So really pretty exciting stuff. The cost of a Mark X is about $69,000. One of the things that Bruce is going to go over in today's presentation is the software which actually drives the printer. So this is kind of a very important thing which most people don't get. So if you look at an Envision Tech printer or a Stratasys printer or something else, the way that they work is they ultimately take plastic and they basically spit it out as a blob. And with the Eiger software that controls the Markforged, you bring in an STL file, and you have the ability, layer by layer by layer, if you want, to specify, is it nylon? Does it have carbon fiber or fiber in it? What pattern does the carbon fiber go in? How much carbon fiber goes in? Is there a void that you would use to insert other third-party materials into the model? And you can kind of see here in this picture that this actually has triangles inside of it. So one of the things that we have the ability to do is to actually put some type of geometry inside of it, whether it would be triangles, hexagonals, or rectangles. And we have the ability to specify what the percentage is in terms of is the model hollow or is the model solid. So we have the ability to solidify the model or also make it hollow. We have the ability to put the fibers in various layers. Here's another view of a cross section. This is a brake lever. A much closer view, and this also talks about the laser inspection as far as going in and picking this. I'm going to kind of go through with some of this stuff. So the new printer has, as I said, it's a surface area. I don't know how clear it is, but it's at 50 microns. And I think you get to a certain point, this reminds me of when digital cameras came out where they were very fuzzy and then everybody was really trying to grapple to get the best resolution or megapixels possible. And ultimately you get to a certain point with megapixels where it doesn't matter because you can't really see it to the human eye. So the difference between 50 microns and 100 micron may not sound like a lot, but to the human eye it's a huge difference. It's kind of like high definition television versus, a Sony Trinitron back in the day. So if you want it, that's ultimately something that happens with the Mark X printer. And also, obviously, it does larger parts. But you look at the surface area, it's really incredible with the parts, really smooth. It uses Onyx or straight nylon. And if you use Onyx, which is what most of these parts, I think all these parts are, then ultimately it's a really nice matte black type finish. So one of the things that we like to talk about, or is one of the use cases, is a lot of people want tooling. They want fixtures, they want jigs, they want a lot of things for production. And ultimately what happens is that in order to pay a machinist to do this or to send the parts outside, they get expensive. And the reality is for approximately 1/10 the cost of a manufactured aluminum part, you can actually go and print this in-house, and it prints overnight, which isn't a big deal. So it's kind of a huge deal to a lot of people because this allows them to use this for production for various types of parts, reduces inventory, supply chain, all this other good stuff. So this printer goes for $69,000. It comes with a bunch of materials that I'm going to kind of glaze through here. And then what we do is we get into the standard Markforged printers, and there's actually 3 other ones. There is a Mark II Standard, which goes for $5,500. There's a Mark II Professional that goes for $8,800, and then finally the Mark II Enterprise, which is the one that we sell the majority of, which is $13,500. That gives you some different options in terms of the software. It gives you different options in terms of all the different fibers that can be incorporated into the model, and it does the, as I said, 12 by 5 by 6 build volume or build size. So that's kind of the lineup. What we do as a company is we find that when people get these printers, like any kind of printer, they actually need to have some education as far as how to service the printer, how do you do some basic maintenance, how do you get the print head unclogged. And these printers, in my opinion, are kind of like a dot matrix printer versus a laser printer. It does take a little proper care and feeding. They do come with a toolkit, so we teach you how to use the toolkit. We teach you how to set it up, how to keep it running properly, and how to avoid any damage. We typically charge $900 for that. And then there's optional annual warranties, and then there's maintenance on top of that. So that's the basic lineup. If you guys want to hear some more, we'd be more than happy to tell you about that. And I think that's really, I'm going to kind of jump onto the Envision Tech thing. But one of the things, it's hard to convey this over the web, but the reality is the parts, you can print them. They're very quiet, odor-free. You can print them from your office, and the parts are as strong as aluminum, which is a whole different animal when you're talking about 3D printed parts, which is really pretty cool to be able to print something that strong. So anyway, I'm going to just jump over this other presentation here, and you can just bear with me for 1 minute, and we're going to switch gears. And I realize there's a lot of stuff, so like I said, if you want something more detailed, we can do that. But about a year ago, we picked up a line of printers which is called Envision Tech. And Envision Tech is pretty interesting because they really didn't have much of a focus on the discrete manufacturing market. Where they were focused was dental, they were focused on hearing aids, and they were focused on jewelry. So there might be a little bit of a crossover with jewelry, but ultimately what's interesting is that they're now taking their printers and we're applying them towards discrete manufacturing and having really tremendous success with it. And the way that printers work, first and foremost, if the printer, if you compare it, I guess just for a 3D printing education, there's really, I think, 2 primary processes in plastic. There's what's called FDM, which stands for fused deposition modeling. So effectively, that's the same type of process where you actually take some solid material, you heat it up, you squirt it out through a nozzle, and you build a part layer by layer. This process here is very similar to that of SLA, which stands for stereolithography apparatus. So very similar, where it actually uses liquefied materials, and it actually cures them either with light or laser. So the way that this works is, if you compare it to a 3D systems machine, what you're going to find is the quality of the model is unparalleled. Nobody anywhere on the planet makes models like these, and the models, just as a comparison, will be able to be made on certain models at 25 micron. So there's 2 primary differences. There's what we call prefactory units. They come in a very small printer that goes for $10,000 to start, and it creeps up here for somewhere around $125,000 for what we call prefactory 4. But what these do is these actually use DLP. So they use digital light processing, which is a technology from Texas Instruments. And what they do is they actually take this and they'll actually shine light, or they'll project light, which becomes very, very accurate, and it becomes very, very tight in terms of the tolerance. So the resolution is such where you can't really determine it on the naked eye. You have to put it under a microscope. So it's unbelievable. Typically, they'll use some variant of ABS. We have 80 different materials plus that we can actually use, which is pretty neat. But really, really unique printer in the market with the DLP technology. Conversely, this line of printers called the Vectra or the Ultra or the Exceed ultimately use a special laser that is a lot less complex than a 3D systems laser, so that means it's less to calibrate it. It self-calibrates, it sets itself up, and it's very, very accurate in terms of what it prints. But these machines typically are for larger format builds. This guy on the left, which is pretty unique, and I don't know if it fits anybody on the call, but it actually is a bioplotter. So what it actually does is it actually allows people to print out any material that they want, typically for biomaterials. So it's things like biomaterials that could be used to build scaffolds to grow an organ. So this is all really space-age stuff. It could be human stem cells. You can actually print out human stem cells, a whole variety of different biomaterials. So it's really kind of open source. You can print your own materials out. It can print them on a heated plate or a cooled plate. And it's something where you would actually put these into somebody's body. It does a really, really tremendous job of printing out silicone as well. So kind of a unique printer, but what's interesting is that these guys are really pushing the envelope in terms of what they have. I'm just going to kind of browse through these slides pretty quickly here. Just give you an idea of what type of customers actually purchase from Envision Tech, and you can see this is a lot of tremendous names. So real quick, as far as the models, you can look at what the build envelopes are and just the general price, but these typically are larger printers to print larger stuff. One of the ways that these actually work in manufacturing is we can actually do investment cast or lost wax casting. So it's really pretty tremendous. So for the part, let's say that Sean showed, and let's just assume that that would be cast out of aluminum, you can actually build that part out of using an Envision Tech printer and ultimately pour hot metal in there and to a piece, use that as a core for the sand cast and actually pour it in there and evaporate the plastic out. You would have that part pretty quickly. So there's a lot of different ways you can do it. You can take a look here at what the build sizes are, as also what the micron size is, as well as what the costs are. So I mentioned there was a ton of different materials. There's over 80. Envision Tech has a partnership with a company called DSM, which has a bunch of plastics called Somos. So really some pretty interesting stuff. They have things from e-glass. They have things with some polyester resin in them where they can actually do a short shot printing. So we have customers that want to go in. They want to be able to print something. Maybe it's a prototype or it's a limited run production, so they can actually give their customers the actual model, and that's what types of things these guys can do. The surface finish of these ultimately are that of a mold, so you really don't need a whole lot of finishing and whatnot. There's not a tremendous amount of post-processing with these. Typically what will happen is they're fairly cured coming out of the machines, and then we'll put them under a UV light curing light, which takes typically a short period of time. But you can see here the extreme line of machines, again, much bigger build plates, build volumes, also much larger price, but it depends on what you want to do. We just talked to a company last week that builds bottles. They need something to actually build the bottles. So this is the 3D bioplotter, and we kind of go through this pretty quickly. This is the Perfactory. So you can see the build envelope is smaller in one of these guys, but ultimately what you get is the resolution is unparalleled. It's very, very simple in terms of the operation of the printer. It's a user serviceable thing because there's really no moving parts other than just the elevator that lifts the parts in and out of the printer. This is the Micro family, and what Bruce is going to do is actually show you this today. So we actually have one of these, and we're going to give you a quick run through of this. So various applications with rapid prototyping. So where I think it's really interesting in terms of being able to actually make hard goods with this. So injection molding. So there's another couple printers that I didn't mention, but I'm going to mention it real quick. So Envision Tech is really, has a broad array of products, but what they do is they actually have a printer that actually prints sand. So what happens is if you want to sand cast something, so they would actually print the sand, the cope and the drag that actually would go through to pour metal into. So really a pretty cool thing, because a lot of people don't want to maintain patterns. They want to make a one-off casting of something. So instead of making a pattern and then molding the sand around it, we actually just print the sand and put the two halves together, and ultimately pour the metal directly in that. So that's called Veritas. That is a printer that's just coming on the market. There's another printer that's just coming to market that's pretty neat, which is called an SLCOM1. And what that printer is, it's a very large-scale production printer that prints carbon fiber. And this actually uses PEEK, which is a really, really high-end superior plastic that has really high melting temperatures. And what it'll do is it'll actually take a roll of woven carbon fiber, and it'll actually pull that to create these panels. And you can make parts that are 2 feet by 2 feet by 2.5 feet. So it's a monstrous industrial grade machine. But if you're building, large scale panels of carbon fiber, then it's a tremendous machine. The only downside, it has $1 million price tag. So that machine is set to come onto the market. That was announced at Rapid in Florida in June, and some really, really pretty interesting stuff. So anyway, I'm going to turn this over to Bruce, which I believe I've done, and we're going to let Bruce give you a quick demo of the Eiger software for Markforged, as well as a live webcam on both the Envision Tech micro line of printers, as well as the Markforged enterprise line. So take it away, Bruce.
All right, good afternoon. Thank you, Gary. Why don't we just start with the web camera and just look at the two printers real quickly, and then we'll move on to a demonstration of the software that drives each one. To the right in the web camera is the Mark II machine. It's a fairly compact machine. It's also fairly rigid. Most of the body of the machine is aluminum. The only plastic part is this lid that I just raised up. It is a fused deposition printer, so the material, whether it's the nylon or onyx, is held in that black case that I just pointed to. And the material is fed through the speed tube through and let me just move my camera here a little bit. The material is fed through a extruder and then onto the print head. The fiber is held in a smaller spool inside the machine, and likewise it comes up through a feeder and an extruder into the print head. The print head has two nozzles on it. The one nozzle is for the base material, whether it be nylon or onyx, and the second print head is for the fiber. Let me just reset my web camera here. The build plate comes off the machine. It's basically aluminum with a Garolite covering. It has some rounded screws on the back of it, which allows you to take it off and on the machine. It registers itself to about 10 microns repeatability, which allows, while you're printing, if you need to drop in an insert, you can pause the printer, take off the print bed, put in an insert, and then put the print bed back on without losing any accuracy. Or if you maybe you're using a fiber and you don't have enough fiber on your roll, you could potentially pause the printer to do that also. The printer can be controlled. The printer is network enabled. My printer is connected to wireless. And because of that, I can send jobs to it from the computer. And earlier this afternoon, I actually sent a job, and I put it in the job queue. And I can just select that to have it start printing. So I'm just going to start printing that a while. And it will take a few minutes for the print head to warm up. Let's just close this and move our attention to the Envision Tech Micro that's sitting here. Envision Tech Micro, likewise, is a very solidly built printer. This one is the smallest unit they have. The build plate for it is this little unit. Just take off and hold down here. This unit has a build size of about 65 by 40 millimeters. But the build plate is this unit I just took off. If I put it on top of the machine, the material, unlike the the Markforged, where the material is solid, the material for the micro is a liquid polymer, which is held in this, what they call the PSA. The PSA has a transparent bottom, and there's an ultraviolet laser which shines a DLP, well, the DLP projector, I'm sorry. They shine a DLP image up through the bottom of the transparent bottom, and that's what exposes the photopolymer resin. Okay. So to start this printing, I'm just going to close the head. Via the control panel, I'm just going to home the printer. So at this point, the print bed is rising up, and then it will then start lowering. At this point, I'm going to turn my attention to the computer. I'll just keep my web camera there so that you can maybe see what's happening. Watching the Markforged print is sort of like watching grass grow. Watching the Envision Tech print is sort of watching paint dry, because not a lot happens. All right, let's move on to a demonstration of the software while starting the print. I'm going to, we'll start first with the IGA software, which is used to control the Markforged printer. I'll log into the website. The software is Chrome-based, and it's basically cloud-driven. And these are basically the parts, and this little square bracket is what I'm currently printing. Okay. Because we're short on time, let me just import a job. Gary showed you in one of the slides this motorcycle brake lever, and I'm just going to use that as a sample part for this Mark II. Via the app, I tell it what material I'm going to use, so I currently have Onyx loaded machine, and I'm just going to tell it to process the part without any fiber, just to give you an idea. And while it's processing, you notice on the web camera, the print bed is raising on the Markforged machine, and it should start printing. Okay. Likewise, it looks like the print head on the Envision Tech has homed itself. So I can actually, the Envision Tech actually allows me to actually look at the control panel via the network. And so I'm already chosen the job. I'm going to just print this base part. And when you select the part to print on the Envision Tech, you can actually see the images that it's going to project on each layer. So I'll just open that up and just start the job. So it's going to warm up the projector. It takes about 30 seconds to do that. And then it's just going to start projecting the images. So let me just minimize that. All right, moving our attention back to the IGA software. It did process this part. It gives me an indication that it's going to take 4.5 hours to print, and it's going to use about 20.29 cubic centimeters of Onyx material. I can actually go into the internal view, and here we can actually see what the internal structure of this part is going to be like. And it's probably easiest to just go into the 2D view. The general construction of the part for the Markforged is to start with about 4 layers of solid nylon on the top and the bottom of any horizontal surfaces. And then after that, it's generally, the part is filled in with a sort of a fill pattern, in this case triangles. You can also fill it with rectangles or hexagons. We then get a 4 layers of material at the top of that horizontal section, and then there's that little box part. At this point, I'm going to tell it to use fiber. You know, I have carbon fiber in my, let's switch the fiber type to carbon fiber. I'll tell it I want to put 6 layers, let's just move it up to 8 layers, and I want to use 200 concentric rings. Now when you're laying fiber in the part, the fiber can either be laid concentrically, where it starts around the outside perimeter of the part and spirals inward, or you can lay it in what's called isotropically, where you each layer is laid in a straight line pattern parallel to each other, and then each layer you set by a different angle, and so you have those 2 different fiber pattern types I'm using concentric. At this point, I'm going to save the part. It's going to reprocess it, and after it does that, I'm going to look at the internals of it, and we're going to see that it was able to put fiber at the bottom of the part, but it was not able to put any fiber at the top because it considers the top of the part to be this little boss area. But that's not really where I want the fiber to go. So I can go into my 2D view, and now I can customize the layout of this part. And I'm going to go to the first triangle layer underneath the full layer at the top of the part. And via the menu on the right, I'm just going to tell it to use fiber. So since I told it to use 4 layers of fiber, well, I told it to use 8, and it puts half of that at the top and half at the bottom. It only gave me 4 at the bottom, so I'll put 4 layers here at the top for symmetry. And notice also, if I wanted to, I could, in the menu, there's a pause after the layer, which would allow me to, when the machine got to that point, it would pause to either allow me to drop in an insert, or if I didn't have enough material on the spool, I could pause the machine to change material. If I'm happy with it, I'll just save this, and it gets put back in my library. To print the part, you simply pick it, and then you hit the print button. And you can, via the this menu, you can control what where you're going to send the printer. Our company has 3 printers. 2 of them are currently offline, and the one I'm currently printing you see in the web camera is Vulcan. So I really can't send it directly to any printer, but I could add this to the queue. And then once the part on the printer is done, I could just start printing it from the queue. Okay. You can also add additional parts. So if I move this back a little bit, I can say add maybe another one of these. And I can print multiple parts. I could save it as a build. So you can have a library of different builds in the past. Let's see, what else? Overhangs, let's just look at this part. If a part needs any support structure, the support structure is printed using the same material as the base material. And if we look in the 2D view, there's in this part, there's some areas here that need supports. And these are the paths for the support material, and it lays in the support material in a sort of a serpentine pattern, which makes it extremely easy to remove. So once the part's printed, you generally either by hand or sometimes I use a pair of pliers, just grab the support and they rip right off the machine, rip right off the part. All right, I do believe that's probably covers the Envision Tech or the Markforged Eiger. Again, the Eiger is cloud-based. You can have multiple users, so multiple users in your company can have access to it, and you can rearrange your parts for your project, and it's fairly easy and straightforward to use. All right, with that, let me just minimize this and look at the Envision Tech Micro. To process a job on the Envision Tech Micro, it's quite a bit smaller machine, obviously. So I'm going to use this proprietary RP software. And I already set up it to do a build, but I'm going to import an STL file first. So with this, I'll go and pick this. I have a Lego part. Everyone knows what Legos are. So if I come in there, it's sitting on the build plate, but I might want to rotate it a little bit. So I'll come in here and via the software, tell it to maybe rotate it -90. No, let's do it the other direction. Let's go back in the top view and just move it up here onto, so it's sort of in the middle of the build platform. And now I'm going to, under the filter, I'm going to actually place it 3 millimeters above. And the reason I'm doing that is so that then I can build a support structure underneath it to support the part. Since Legos are hollow, it needs supports underneath there. So I'm going to choose a support that I want to use, and maybe I'll use this guy here. Now, if I click on this, I can actually see the geometry of the supports. You can adjust the geometry, how thick and how tall and wide they are, and how far apart the supports are spaced. I'm just going to just accept that and then have it start building the supports. So if I zoom in, I can see where they are. If I'm happy with them, I'll just basically click. All right, if I'm happy with this, under the file pull down, I can actually build the job, and I'm going to pick this directory to put the job into. And it's going to process it. And what it's doing is it's actually slicing each layer And instead of generating full paths, which your typical FDM printer is generating, software is generating, instead what it's doing is it's actually constructing layer by layer a set of images that it's going to use to project to build the part. So once I've built it, I can actually examine what that part's going to look like in this factory job inspector. And likewise, let's just open the file, and it is going to go to where I put my jobs. There it is. And let me expand this. So I can actually step through the layers, and what we're seeing are the actual images that it's going to expose the plastic. And once I get up here a few bits, now we see the exposure of where the Lego block actually starts. And once we get to the top, we start seeing where the block of the nibs are on the Lego. So you can examine what your build is like, and then you can either transfer it to the printer either via USB, or if you have the, I don't currently have it, but if you have the printer added as a drive on your computer, you can do a drag and drop to move the build file over to the printer. If we go into notice here, if I open up the printer control panel, notice it is actually printing that job that I told it to. It looks like it's currently on layer 41 out of 811. And while we can see the printer Markforged print head moving around quite a bit, you're not going to see too much movement out of the Envision Tech. Between each layer, it moves up. The print bed moves up about 1/4 inch and then back down, and it's a little bit slower process. All right, with that, why don't we open the floor for questions?
I think we're doing a pretty good job today because there are no questions at this time.
Either that or we've confused everybody, Rob.
Hopefully not. All right, so if there's no questions at this time, it's pretty simple to get in touch with us. You can send us an email at info at 3hti.com. So we do have a question concerning the cost of supplies and what's needed. So my question is, which printer is that for? Is that for one of the Envision Tech printers, or is that for the Markforged printers? For the Markforged printer. Gary, I didn't know if you had a had the presentation still.
Let me see if I can. I'm not sure if I have a presentation handy. Hang on just 1 second, Rob, and we'll I think if I can pull this up, it might be a little bit easier. I'm not sure.
Well,
I have the up. Yeah, hang on, let me just see. Yeah, let me just share my screen real quick.
Yeah, I just turned you over.
All right, sounds good. And unfortunately, this slide hasn't been updated yet, but I'll just go off of it. So what you can see is that you can see the different spool sizes. Now, this spool size for nylon has been changed. Unfortunately, the slide doesn't reflect it. It's actually now 800 cubic centimeters. And the price for this is $170 for 800 cubic centimeters. All the other consumables, the fibers, all are at increments of 50 cubic centimeters. And as you can see here, carbon fiber is 150, Kevlar is 100, fiberglass is 75, high temperature, high strength fiberglass is 100, and then finally Onyx is 190. And again, that's the nylon here, which is just straight nylon, is 170 for that. Now the thing about the materials is you typically don't use that much fiber in a model. And the other thing is that typically you don't really use that much nylon because most of the time you would print the part that wouldn't be completely filled. So whatever that's worth, one of the things is that people always wonder, hey, how much is it going to cost? And a very simple thing that we do is we get an STL file from a prospective customer. We put it into Eiger software. We, try some different combinations of how we might think it would be best manufactured. And then we can give you a simple price or demo that to you. So anyway, that's kind of how that works, but hopefully that answers your question. Any more questions, Rob?
That was the only one. Just supply costs.
Excellent. So if that's not it, I guess we can adjourn, Rob. We actually finished in pretty quick. Sorry about the speed of going through this thing. As I said, we wanted to show you SolidThinking and just try to give you a quick overview of what we offer from a 3D printer perspective.
Well, thanks everyone for being on today. Gary, Bruce, thank you, and also thank you, Sean Kroger, for being a part of this today. I hope this was very informative. We will be back in a couple more weeks with another 3D printing related webinar, and we look forward to seeing you then. But once again, reach out to us at info@3HTI if you have any more questions, and if you would like to see a replay of this video, you can email us at info@3HTI also, or just respond to the email that you received confirming your attendance to this webinar. So thanks again, everybody, and enjoy the rest of your week, and have a great Thanksgiving. Take care.
Thank you.